Alright, today we're going to be working on Proposition 15. And Proposition 15 is going to be, I think, probably the longest proposition for a long time, or at least until we get near the end of Book 1. So, personally, I have to go on a plane in like 2 hours, and I don't have time to memorize all this stuff because, as I'll show you, this is a long one. So I've written out the steps that are in the book, but I've also written out little explanations. Our construction I've already completed, and I'm not going to go over every step of it, but basically what you need to know is that we have an ellipse, and AB is the diameter of that ellipse, and AN is our kickstand. So that has all been set up, and then we set up this other diameter through the point C, and the point C is bisecting AB. And what we're kind of trying to do is see if DE can be a conjugate diameter. If you remember from the definitions, a conjugate diameter is one where GH is parallel to AC, and these lines are ordinate-wise to this diameter, and at the same time, GX is parallel to DE, and these lines are drawn ordinate-wise to AB. So they have that sort of reciprocal relationship. So DE, we don't know, is a conjugate diameter yet, but we're going to try to prove it, and we're going to do two things to do that. The first thing is we're going to set up DF as a sort of supposed kickstand, and we're going to prove that lines drawn potentially ordinate-wise to DE, like for example GH, the square on DH is, or square on GH, is equal to the rectangle HLMD, because that's the relationship that we have with a regular diameter. And then the second part is we're going to try to prove that GH is drawn ordinate-wise. And if GH was drawn ordinate-wise, then by definition, if we extend it through to W, GH will be equal to HW. Because ordinate-wise lines, what that means is that when they're drawn through, they're bisected by the diameter. So those are our two things that we're trying to prove. The first one is the square on GH is equal to the rectangle DL. Okay, so let's start. Triangle ABN is similar to triangle TPN, which is similar to triangle CPB. You know, this drawn parallel to this drawn parallel to this. Easy enough. And that means that BA is to AN, as BC is to CP, and PT is to TN. And CA equals BC by construction of where we put C, and CA equals TP because by construction AC is parallel to TP and AT is parallel to CP, and in a parallelogram the opposite sides are congruent. Okay, so now this is the tricky step. We want to prove that the area AP is equal to the area TR. So what we already know is that TP is equal to AC. But we don't know anything about this line TN. But we also know that AT is equal to CP. So we're going to use our triangle ratios, and BC is to CP, BC is to CP, as PT is to TN, so PT is to TN. And if we know that this relationship holds, and we know that BC is equal to AC, and AC is equal to TN, then we know that TP is equal to BC. And these two lines have the same relationship to these two lines. But we know that CB and PT are equal. So CP and TN are also equal. So those are the unstated steps there. But now we know that these two lines are equal to these two lines are equal to, in the same ratio to these two lines. And this is equal to this, and this is equal to this. So base times height means that these two areas are equal. Great. And then area XT is equal to area TU. So this is XT, and this is TU. Because these are parallelograms, AX and T unlabeled point are going to be equal because they're opposite in the parallelogram. And we already proved that AT is equal to TN, so base times height again, those two areas are also equal. Great. Okay, so we had that XT is equal to TU. Now we'll do OT, draw this, is equal to OR. Now I'm not really sure if you're familiar with Euclid, but in Euclid, if you have a parallelogram and you have a diagonal line through it, and you just drop any line parallel to this one, and then where they intersect, you draw another line parallel to this one, then he proved that this area here is always equal to this area here. And that is the exact construction that we have here. So we know that TO is equal to OR because they're what's called parallelogrammatic complements. And then we are going to add the area NO to both of those things. So now we'll have TU is equal to SN. And then from up here, we'll bring that down. XT is equal to TU. And let's see, area NP is equal to area PA. So that's NP PA. Oh yeah, we proved that before. So area TU plus area TS is equal to area NP. Okay, so what we can see here is that when we've drawn these two areas, this part, TO, was an overlap. We drew that twice. And we know that TO was equal to OR because they're parallelogrammatic complements. So imagine moving one of those areas over to here, and that would make this whole area. And we've proven before that that whole area is equal to this whole area. So that means that this area plus this area is equal to this area. And area NP is going to be substituted for area PA, as I just said. I kind of jumped the gun there. Area TU up here is going to be substituted for area XT. And then this area TS is here, and that's made up of TO and OP. So we're just going to rewrite that as TO plus OP. So we substituted out each of these terms, and that's that step. Now let's see. We have xt plus to equals AO. Well, that's xt plus to equals AO. That makes sense. And area AO plus area PO is area PA. Okay, so I think that's reliant on the idea that xt from before is equal to tu. So I'm going to sort of redraw this out. So we've got this area, we substituted it for tu, and we've got po. And then once again, just move this area to to this area or, because we know that they are parallelogrammatic complements, and that will make it equal to this whole area tr. I hope I'm not doing this too fast. And of course tr is equal to pa. So that's easy enough. And so we have, oh okay, I see what we're doing. All we've done is subtract AO on both sides. So instead of AO plus PO, it's just PO on one side. And on the other side, instead of PA, it's now PA minus AO. And area PA, which is this, is equal to the square on CD. This is an ordinate. It's not a square, but just, you know. And the area AO is equal to the square on XG. Another ordinate. So those two things fall out of 113, where if you have an ordinate drawn to the diameter, then the rectangle on that part of the diameter is equal to the square on the ordinate. That's going to become pretty everywhere, that concept. But we had that like a couple of videos ago, so you can just reference that. And then area PO is equal to rectangle OS SP. That's just from saying that you could write this as area PO, or you could just write PS times OS, base times height. It's the same thing. And then we have the square on CD. Oh, okay, I see what's going to happen. We're going to substitute. So I think this is what we're going to substitute from. And area PA, we're going to substitute that out for area CD. Bring that down. Minus area AO, we're going to substitute that for XG. Bring that down. And area PO, we rewrote that as OSSP. We bring that down. So that's just substitution. Alright, step 3. So DE, the line DE, which is the supposed diameter, is cut in equal parts at C and unequal parts at H. So this equality falls out of that, and that's from Euclid Book 2. I don't think I'm going to talk about that any further than that. You can look at Euclid for that. And we have CH is equal to XG. That's CH and XG. This is the same thing where we constructed these two parallel, we constructed these two parallel, opposite sides. I'm saying that a lot in this one. So then we have, we're going to substitute, well, we're going to bring this one down. and we're going to substitute ch, the square on ch, for the square on xg, because ch equals xg, and bring down cd as is. Great. And then we're going to move xg over by subtracting it from both sides. I think that's pretty visually obvious here. Last time I rewrote it strangely. And then from the previous step, this thing right here, we have CD minus XG equals rectangle OSSP. And then over here, we also have the term CD minus XG. So that means that rectangle EHHD is equal to rectangle OSSP from substitution. Great. Okay, so when we constructed DF, we constructed it similar to how we would do a kickstand or an upright side. I keep saying kickstand, but that's just my language. I should probably use the correct one. So that's given. And okay, so this is from Euclid 619. I will sort of try to say what this is about because this one's tricky. So as DE is to DF, the square on DE is to the square on AB. And that's from the idea that if you have any ratio set up like this, where the two middle terms are the same thing, then you can imagine it like as 2 is to 4, 4 is to 8, something like that, right? If you have this, then as 2 is to 8, taking the extremes here, the square on the first term is to the square on the second term. So as 2, if 2 is to 4 is as 4 is to 8, then as 2 is to 8, 2 squared, 4, will be to 4 squared, 16. I just like to use the numbers because you can see how that works out. But it's just a principle from Euclid. So we're doing that here. We took DE, we took DF, and we are saying that they are as to the square on DE is to the square on AB. And now we are doing as the square on DE is to the square on AB, the square on CD is to the square on CB. Let me just look at that diagram. So we've got DE, AB, DE, AB, we guess it's going to be DCCB. Yep. DCCB. So if you have one thing is to another thing, then you have half of that thing is to half of the other thing. I think that's pretty intuitive, so I'm not going to explain it further than that. So then we're going to substitute. So we've got DEAB here. We've got DEAB here. So we're going to bring down DEDF. And then, oh yeah, that's the only part of the substitution. For some reason I'm always expecting these to be more. So we just bring those two terms down also. Great. So we have rectangle PCCA equals rectangle PCCB. That's because CA equals CB by construction. So you have equals times the same thing are also going to be equal. And then you have the square on CD equals the rectangle PCCA. The square on, what did it just say? The square on CD equals the rectangle PCCA. It's because CD is an ordinate, and 113. So PCCA is here and it's here, so we're going to substitute it for PCCB and bring down CD. And then up here we're going to bring down DEDF, and then this part, CD to CB. I guess all we're substituting is CD for rectangle PCCB. Yeah, that works out. So now we have, as DE is to DF, EH is to HL, DE, DF, EH, HL. So it's one similar triangle within the bigger similar triangle. So their sides are, can be put in that ratio. And as EH is to HL, rectangle EHHD is to rectangle HLHD. Without even looking at what any of those lines are, I can just tell you that because it's EH multiplied by HD and HL multiplied by HD. I think sometimes it's tricky to think of this as multiplication when it says rectangle. You want to think of it as an area, but yeah, it's just values, right? Lines are just values. So then you have DEDF, bring that down, and then EHHL is here, so we're going to substitute that for the rectangles, and I think that's easy to see. So now let's see. Okay, I see. So it's like DEDF, these rectangles, DEDF is these rectangles. So as DE is to DF, you have these rectangles in square, and these rectangles in square. So this is just substitution, because the unsaid step is that as DE is to DF, DE is to DF. That's insane, right? Okay, so we substitute on both sides. Now we've got as PC is to CB, PS is to OS. Let's try to remember that. PC, CB, PS. PC, CB, PSOS? Was that it? It must be these triangles are similar. So I believe it. And then as PC is to CB, we have PC multiplied by CB and CB multiplied by CB. So that's going to retain the same ratio. And then as PS is to OS, we're going to have PS multiplied by OS is to OS multiplied by OS. Same exact thing. And then we have substitution. For PCCB, we're going to bring down these rectangles. And for PSOS, that's here, and we're going to bring down these rectangles. Now let's see. PCCB is to square CB as rectangle is to rectangle. That is this from earlier. Just rewritten. Nothing changed about it. So we're going to do substitution because these two terms are the same. So that means that we're going to bring down this on one side as PSOS is to square OS. as EHHD is to rectangle HLHD. Oh, so now step 3 is going to be relevant again. Rectangle OSSP equals rectangle EHHD. So we'll just rewrite that. Already forgot how we even got that, to be honest. So OSSP is just written differently here, but it's here. And rectangle EHHD is written the same and it's here. So equal thing is to something as equal thing is to something. So if they have the same ratio, then you would expect that square OS and rectangle HLHD would be equal to one another. In fact, they have to be. So we write that down because equals have the same ratio to equals. Okay, let's look at OS, XC, GH. OS, XC, GH. Okay, so this is drawn parallel to this. This is drawn parallel to this. These lines constructed parallel to one another. These lines constructed parallel to one another. So you can sort of bridge the gap with the line XC that GH and OS are also equal to one another. So the square on OS is equal to the square on GH. And then we bring down HLLD, still HLLD. So this is kind of a anticlimactic ending. Square on GH is equal to rectangle HLHD. Let's look at what that is. So that's the square on GH is equal to the rectangle HLHD. So that's as if GH is acting as an ordinate to this diameter and DF is acting as an upright side to that diameter. So this might be a conjugate diameter to the diameter AB. But we would only know that, and in fact we only know if it's even a diameter and if this is even considered an ordinate, if it's drawn ordinate-wise, if GH, when drawn through it, is cut by the section so that GH is equal to HW. So that's the next thing that we need to prove, and if we do prove that, then we would prove that DE is a conjugate diameter to AB, sort of by definition. So we have 1/2 the proof. Okay, so this is just me writing out what I just said. Okay, so let's look at GX and WY. That's GX, WY. This is constructed parallel to this. Blah, blah, blah. You know what I'm going to say. Great. So that means that the square on this is equal to the square on this. So the square on GX is equal to the rectangle AXXO. That's the square on GX. It's equal to the rectangle AXXO. I think I said below, like in a note, that we proved this above, but no, it is from 113. I think I was confused at the time that I was writing that about what diameter was what. But that's the square on the ordinate, the rectangle on the diameter with a kickstand. So that's true. Same thing for WY, it's just that WY is over here. So the square on this would be equal to the rectangle YZAY. It would be something like that, maybe. also from 113. So if gx is equal to wy, and gx is equal to this, and wy is equal to this, then these two things are equal to one another. So that's what we wrote. It's substitution. Okay, so I always feel the need to explain means and extremes, even though I think I've probably explained this 2 or 3 times now. This is what I find least intuitive, maybe. So means and extremes just means that x, y, z, a, if you have a ratio set up like this, then x times a is equal to y times z. But that also means that if you have x times a and y times z, that you could write a ratio out, like you could write x a needs to be on the extremes, and y z needs to be on the means. Although you could, once you have it like this, if you're doing reverse means and extremes, the order doesn't matter. So you could, for example, write zy, and that would still work out. Even though it's yz here, zy, doesn't matter. It's just that if you have, I'm going to call this a rectangle, but it's just 2 magnitudes multiplied. One term needs to be separated on the extremes, and one term needs to be separated on the means, meaning the middle terms. Great. So AXXO is 2 magnitudes multiplied. We put XO on this extreme and AX on this extreme. Same thing for AYYZ. We put ZY on the mean, YA on the mean. So that's proper reverse means and extremes. Now let's look at OXZY and XBBY. OXZY, okay, let's look at this. OX XB BYYZ. Is that correct? Let's just check. Yes. So that's just a tiny similar triangle instead of a large one. So over here we have OXZY, we have this term again, so we're going to on one hand bring down this term over here, and on the other hand bring down this term over here, because as OX is to ZY, OX is to ZY. That's the implied step there. Oh man. Okay, and YA and XB, let's look at those lines. YA is the same thing as AX plus XY. And XB is the same thing as XY plus YB. So we're going to keep that in mind. Yeah. So, separando yx is to ax as yx is to by. So what we're doing is we're taking this step here, and what we're doing is ya minus ax and xb minus by. That's what separando is. I kind of wish I had a way to explain this like I do with means and extremes, but it's always like a first term minus the second one, second term minus the last one, and in this case ya minus ax is yx. So we're going to substitute ya with yx, and xb minus yb is xy. So we substitute xb with xy or yx, and we keep the second and fourth terms the same. So that's the process of separando. I don't have an easy way to explain how it works, but you can always reference Euclid. So yx is here and yx is here, and they are obviously the same thing. So they're equal. So that means that ax and by are also equal. So ax equals by. And AC equals CB because we placed C in the midpoint of AB. So that means, let's just remember AX and BY. 1 second, let's go up. So AX equals BY and AC equals CB. So that means these remainders XC and CY must also be equal. So that's what we're doing. XC, CY are equal. So if XC equals CY, then GH equals HW. Because XC, CY are here, GH, HW are here. They are in these parallelograms opposite one another. So that means that they're equal. And the force of them being equal is that it means that GW is bisected at point H. And point H is where it cuts DE. So that means that if DE is a diameter, then GHW is drawn ordinate-wise to that diameter. And that was the second part of proving that DE is acting like a conjugate diameter to the diameter AB, that DF is its kickstand. So, I'm going to start packing now.